Hello and welcome to Calculus1.
Yeah. Hello and welcome back to Calculus 1. We are starting chapter 5. We are going to discuss integration. We have 5 sections to talk about, and these will be just basics of integration. We already know how to do some of the mechanics in terms of integrating basic functions, but now we're going to add the meaning and scratch the surface of application for entire chapter of integration. The integration will be studied excessively in Calculus 2. You'll have 2 chapters, one on application and one on mechanics, right, or how to integrate. The first order of business is to approximate area under the curve. You all know, hopefully, how to find the area of the triangle. You know the formula, right? What's the formula for area of the triangle? 1/2 base times height. Great. Now, we're not going to use that. Cool for you to know. What we are going to use is the formula for area of the rectangle. Now, what's that one? Base times height. Good. So area of the rectangle is base times height. This rectangle is not too happy. Someone better. All right. So, as I mentioned earlier, and you told me the formula, if we have some kind of a XY graph, we hit the line here that goes through 3 and through 5.5 as it appears on my graph. You can find the exact area by using the formula area equals 1/2 times 3 times 5.5 is 11 halves. So this is 33 over 4 altogether, or 8 and 1/4. So you can find area under the curve exactly if the shape is something that you know formula for. But what happens for the curved functions? What do you do when you have a function that looks like this? It's some f of x, and you want to compute the area under the curve. Yes. So what we are going to do here is we are going to approximate the area by cutting this area here into these rectangles. And we are partitioning our domain from x0 through x1 through x2 to x3 to x4, which is a to b. We are partitioning this domain, and what I'm going to do is I'm going to create these rectangles using the left point. Now, I hope you guys see that we have 4 rectangles to work with. And calculating area of each one of these rectangles is very easy, but we need numbers. So what I need is the length between x1 and x0 and x1. We call that area, length, delta x, because that's a change in x from x0 to x1. So if you are looking at this particular picture, you are immediately able to recognize that you can calculate delta x by simply subtracting a from b and dividing by the number of rectangles. So as you're looking at this, right, you're looking at this, the delta x for this particular problem here, in general terms, would be x4 minus x0 divided by 4 rectangles, whatever those numbers are. And now, if you notice here, this point on the y-axis is f computed at x0. This point here is x1 and f computed at x1. And then you have the next point, which is x2 and f computed at x2. This one is x3 and f computed at x3. So all of these points are known because you know what the function is, and because you already have x0, x1, x2, and so on, you can quickly compute y1, y2, y3, and so on. So we have all of those points. So now if you take a look at any of these rectangles, we'll take a look at the first one here. What you clearly have is the, right, to calculate the area of that rectangle, you know that it's going to be area 1 is equal to the delta x, which is the width on the base, times the function computed at x0. Because you have the width times the height, a times b. Area 2 is delta x times f of x1. That's the second rectangle. If you carefully look at it, the height for that rectangle is given by f of x1, right? So that will be the y value. And each one of these is delta x. They're all the same, right? All the widths are delta x. So by that token, A3 is delta x times f of x2, and area 4 is delta x times f of x3. Note that f of x4 does not play a role because there is no rectangle to its right. We use the left-hand points. And because we use the left-hand points, that means that the rectangle is to its right. And then x4 does not have a rectangle to its right, so it has nothing to do with our calculations. Now we add all of these, and we say that the actual area is approximated by the summation of all of these other areas. Clearly, the answer is not going to be exact because, look at this, guys. The red stuff is error. We are overshooting the actual area. We are overshooting because we are trying to approximate this curve. We don't know how to deal with that stuff. We don't know how to deal with a curve. But what we do know is how to deal with a rectangle. So if I use the left point to create a rectangle, that rectangle is bigger than the actual area. It's a trade-off, right? Easier to compute, but then not exact. Yes?
Is there a simple way to get rid of the error? Because it seems like that error adds up to be a fair amount of area.
Oh yes, that's the next step. So we are going to compute the area here, and we are going to actually know that the true area is less because we have all of this extra error there. Now the question is, can we do better? Yes. If we make more rectangles, if this dx is smaller, we will have more calculations, but that will have less error. So if I go now and draw the same picture, but with the double amount of rectangles. So I will start now with this picture here. To be something like this. So this is the old situation. Yeah. So So guys, this is the old situation. Now what I'm going to do is I'm going to split each one of these into half. So I'm adding twice as many. Guys, the first rule of engineering is draw big. If you are in your notes and you are doing this, by the time you put all of these rectangles, it's going to look like this, and that's just useless garbage. Right? Try to make this as large as possible in your notes so you actually can see when you draw these rectangles where the areas and error is. Now I'm going to label all of the left points. Note that I have 8 rectangles now. And now I'm going to draw rectangles. Now, for the split moment, I'm going to use the red to show additional error that we had last time. So, what's enclosed in these little areas here is the new error. What's in the red, under red, is old error. You see how much better this is. We doubled the amount of rectangles, and the error, a lot of error, disappeared. So, conclusion is more rectangles implies less error. What's the trade-off? More rectangles leads to more work. Yes. This is how your software integrates.
What kind of software do this calculus use?
Mathematica,
Okay.
Desmos, Simulab, Maple.
And I can do an infinite number of this, right? So once the error is divisible.
Yep. So now it's more work. We are starting at x0, x1, x2, x3, x4, x5, x6, x7, x8. There is 9 points there that are enclosing 8 rectangles, 8 areas now to be added in comparison to the 4 last time. But thinking about this, guys, you have less error with more calculations. And now let's extrapolate. If I double the amount of rectangles and make it into a 16, it's going to be even less error. How many rectangles do I need to have exact area calculation?
Infinite number.
Infinite number. So here, I'll write in here purple. To have exact area, we need infinitely many rectangles. We'll need infinitely many rectangles to do that. And we are going to actually use that next class to show. So what I'm going to do now is I want to find out, oh, by the way, and all of this can be done also for right points. So we'll deal with that. Let's do an example. Approximate area under the curve f of x equal x squared plus 3 from, well, actually on interval, so on 0 to 4 with n equals 6 rectangles. So where do we begin? Draw. Is what?
N is equal to the number of rectangles.
Yes.
Each rectangle at 2/3.
Yes. So I have 1, 2, 3, 4, 5, 6, 7, 8. I'm going to use 8 divisions, so each one is the unit. Draw big, right? So here's the 0 and here's the 4. So those are my A and a B. How much is delta x? Delta x is 4 minus 0 over 6, which is 2/3. So I get to draw a rectangle at every 2/3. What are the numbers? The first rectangle, so we have A and B, so it's 0. The first rectangle is at 2/3, and then plus 2/3 is 4/3, and plus 2/3 is 2, and plus 2/3 is, so that's 8/3, and then 10/3, and then 12/3 divided by 3 is 4. So these are my points. You get to partition this using a simple division, and then you keep adding fractions if you end up with fractions. Now we draw the rectangles using the left point. You can also use the right point. And we see that the area that we are going to compute is actually going to be smaller than the actual area. But such is life, right? We are approximating. So what is the area of the first rectangle? It is going to be our delta x times the function computed at 0. Plus the next area for the second rectangle is computed at 2/3 plus delta x f at 4/3 plus delta x computed f computed at 2 plus delta x f computed at 8/3 plus delta x computed f at 10/3 plus delta x, oh no, that's it. We have 6, right? 1, 2, 3, 4, 5, 6 rectangles. So we have 6 separate areas. We need to add them all for the total area. Now you remember that your f of x was given as x squared plus 3. So now each one of these has to be calculated. But before I do that, do we all see the delta x factors? Right? And you just have f of 0 plus f of 2/3 plus f of 4/3 plus f of 2 plus f of 8/3 plus f of 10/3. See you next week.
See you tomorrow.
Now we plug everything in. So delta x is 2/3. And then we do all of these calculations. We have 0 squared plus 3 plus 2/3 squared plus 3 plus 4/3 squared plus 3 plus 2 squared plus 3 plus 8/3 squared plus 3, and finally 10 over 3 squared plus 3. Zero squared, it's nothing there, right? First of all, we have 3 times 6, that's 18, right? Plus, those are all the plus 3's. 2/3 squared. When you start squaring these guys, oh, I forgot. It's, yeah, 4 9s. Don't cancel if you can, because they all have the same denominator at the end. So we have 4 over 9 plus 16 over 9 plus 4 plus 64 over 9 plus 100 over 9. 4 you can add to 18. Right, to get 22, and now 100, and this is 84, 184 over 9. Common denominator, so now this is just middle school. So that's 198, right? Over 9 plus 184 over 9 is equal to 2/3 times, that's 382. Over 9, and our approximation is 764 over 27. You can divide this in the calculator if you want. So we were able to approximate the area under the curve, and we know this is not exact, but we can say it's good enough. You want better? Redo the entire procedure for 8 or 10 or 30 rectangles. Depends on how much calculation you want.
Is there like a standard unit that you apply for that unit?
You can just say units squared, because it could be centimeters, millimeters, inches, miles, right? It could be anything. So units squared, because we're talking about the area. I want to call your attention to this. Yes.
How do you know how many like sections you should or rectangles you should use?
N equals 6 given. Right?
But the more rectangles you use, the closer it's to it.
Yes. So there is a trade-off between how many calculations you want to do and what precision, or you're just governed by what precision you need, depending on what you're making, what you're building. Your precision for money is at most 3 decimals. When you go to the gas station, they tell you that the gallon of gas is $3.29 and then 9 over 10. That's 9 over 10th of a cent. I ask for change every time. So that's the most that's the most you know, that you deal with, unless there are exchange rates for money, you know, between different currencies and so on. But you know, business world does have that. Guys, I want to call your attention to this. See that? This one that was factored out, and all of this represents a function because all of these guys are under function. This is your dx from your integral in the future. That one right there. And it's calculated the same way, except we don't use delta x, we use dx because it's infinitely small. And we'll talk about that when we get to that the theoretical piece. So I just wanted you to spot that delta x, and that delta x becomes dx for our integration later on. So now what we did here is we approximated area under the curve. And as I said, if you want a better precision, you can use more rectangles. So now I'm going to give you one from the textbook, the homework. And then we're going to start talking about calculus again. So far, no calculus, right? Your function is y equal sine x. Your interval is 0 to pi. And they want 4 rectangles. So this is it. So sine x goes 0 to pi, n equals to 4. So this is just the first bump, right? First bump of the sine graph, and 4 rectangles. Let's see what you get. What happened? Good.
I upgraded my these guys. They're now they're so good. You use balloons. I don't use balloons. I don't have dragons. That see exactly. That's where I build that. I don't have dragons. That's not me. So do you just use those two? Or I'm not there yet. I'm just not at that level. I play so much more to build a base. Right. It is pretty good. It's also interesting seeing how other people put their bases up. I saw this one guy.
No, but I had to think about that.
They've dropped, yeah.
Wait, what? I'm right?
Yeah, you're right. We started.
This is the first time I was here. Oh, man.
The rankings probably change all the time. They probably change. Send me that shit. You know what?
X over y squared is equal to x squared over y squared.
I'm gonna do the two.
He did the same thing on the bottom and wrote China. The guy was second. Yeah.
You might have been like inactive. Like if you leave your base, you will not focus.
I drew it, and then
If you don't play, yeah, you
split pi.
Because you don't read, you don't know.
Pi over
So-
or pi over 4, pi over
Oh, it's this guy.
pi over 4.
He's still
And
second.
then,
Yeah, the other guy had all these things like this is all
But how are they so good if they do that? We need somebody.
This is what I'm doing. Okay.
That's the range.
Next one, I think I looked at 30% from the.
Wait, do you want? Does he want the rectangle?
Verify now if I've been done to drink.
white chocolate.
Yeah, she's
I mean, that's the worst kind of chocolate.
Yeah, she's I know.
It is also not actually chocolate. But also, if you prefer white chocolate to this chocolate, you're out the window.
I know, I heard all about it.
No, I appreciate that because mediocrity.
Oh no, I saw.
The sign graph does the whole upside down U shape, right?
That's also.
Hey, by the way,
Lou's not giving those better lines.
Yeah, I'm gonna hold it honest.
Oh god.
Why do you do this?
Yeah, it's really
Have you never had? Okay, I don't.
No, I'm gonna.
No, we. I mean, I just got your bedroom eyes, and I'm gonna go take a shower right now. So, like.
what's better, right?
Lewis's bedroom rides are more like I'm gonna get.
Yeah, I
No, Lewis's bedroom eyes are. I'm about to get arrested.
Yes, what's the better mind? I don't get the second.
Get 911.
Yeah, call 911.
Are we on a break or no?
No, we're doing a math problem.
I don't even know what we're doing. Don't take breaks up here.
Playing Clash of Clans. We don't take breaks in here.
All classes. Like, don't take breaks.
That's not. That's no. It's not break. It's my grind. Yeah, that's why I come here.
I appreciate that.
Watching Hills.
Where you guys going? I'm going to the room, by the way.
Yeah, he's going to.
What the fuck does it matter? I'm gonna put.
Israel.
Starbucks.
Yo, Ryan.
No, I'll go to
Oh my god, Patreon.
Yeah, no, that's what he just said.
No, it said your girls in the room.
Yeah, no one knows.
Oh, yeah. It's
Shit,
all
there's
right.
girls in the room.
Out the window, out the lane.
Out the window.
All of you.
Hold on. Back to the.
No, it's break right now.
Oh, I guess it is a break.
Yeah, right now.
No, it's like
Yeah,
Hey, baby, you want to have some better lives?
What is it?
So bad. What is it? It's very seductive.
When
No,
you,
it's
like the sexy one.
it's like,
You don't have the sexy.
yeah, we
That's what we're trying to say.
Dude, I don't get the sexy
Get that right there. Right down to it.
Nah, you're watching this.
This is Lewis. It's like, alright, I have about 5 minutes to spare.
I think he's trying to say you early one.
Yeah,
Where are you guys going?
Wait, are you guys going to Subway?
Dude, you guys are always just get like 5-minute breaks.
I'm like,
Yeah, that's how we go for like an hour.
Like,
Yeah, but who am I to say? I leave halfway through the class, right? Let's say you guys give it more.
Yeah, I'm gonna stay. No, I'm staying. I'm listening. If we leave right now.
no, wait, wait.
I'm gonna get my
Chewie was about to fight. He's like, yo, dog, you call me an alien, I'll fucking kill you right now. Yeah, he's like, yo, I'm laughing off. And goes,
Goodbye. Right on it. Ryan, just right here. Goodbye.
Let's take a look. Hopefully you're done by now. So the graph for this is going to be just the first bump of the sine, right? There's another one going later down there. We don't care. We are working on 4 rectangles, so it's safe to say you cut it in half and then each half in half. The values are 0, pi over 4, pi over 2, 3 pi over 4, and pi. All of those values we can compute in sine easily. That's nice. And now we have to decide whether we want to use the left hand points or the right hand points. Right hand, that's fine. That means that each one of these, we are going to pick the right corner and create a rectangle. So the rectangles are on the left. Observe that the last rectangle is 0. But then there is a lot of area that it's error. But there is also a lot of area here, so they kind of equal out. They don't equal out exactly, but you know, approximately they do. Yes.
As far as the practical solving this problem goes, couldn't you just use a symmetry to minimize error?
Actually, in this case, that would not work in this case because look at this. All of this is a lot of error, right? And then this is a little bit more error there. Would you agree that? Now observe that on the other end, for the function, right? You have error in a different way. So this error over here underestimates, this one overestimates, right? Sorry, the other way around. This one overestimates here, and then this one underestimates right there. So they don't cancel each other out, but they help each other out cancel as much as possible. So in this particular case, symmetry would actually preserve error to be only one way and without that equalization. All right, so what is the area approximated by? So I have my delta x, which is pi minus 0 over 4, which is pi over 4. And we see that pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4, and 4 pi over 4 is pi. So, delta x computed at f of pi over 4 plus delta x times f computed at pi over 2 plus delta x computed at 3 pi over 4 and one more plus delta x of f computed at pi. We are factoring out delta x, which is pi over 4, and we are left with sine pi over 4 plus sine pi over 2 plus sine 3 pi over 4 plus sine of pi. Pi over 4 times root 2 over 2 plus 1 plus root 2 over 2 plus 0. And we're getting pi over 4 times 1 plus root 2. That's it. Now you can go and you can get the decimal if you want to in the calculator. It's not something that we really care about too much. So we approximated, and as you can see, guys, we use the right hand points this time. So because we use the right points, this over here ended up being a 0. So this whole rectangle did not contribute at all. All of this area here was error because it is clearly the part of the area, but none of it was calculated, which was made up by overshooting the area by this much on the other side. Can we do better? Sure. Put more rectangles. But the issue here is that if you double the amount of rectangles, you are going to end up at pi over 8. Exactly. What's the sign of pi over 8? You would have to invoke the formulas for to compute this, the half-angle formulas. Yeah. So it will be really pain in the neck. Not worth it. However, you could do 6 rectangles, right? Because that would make you pi over 6 and then pi over 3 and 2 pi over 3 and so on, right? So that could be possible, and you can compute that. But then you're going from 4 to 6 rectangles. Yes, you're getting a little bit better, but not, you know, the trade-off there is not that great. You at least want to double it, right? But doubling the number of rectangles would make a huge mess. And then if you do double that, you're ending up with pi over 16. Good luck with that, right? So you see that, you know, there's always a trade-off between calculations that you are willing to do and then these on. So now we're going to mainstream. Do you want another example or
Yeah, please.
one more? Now, I'm going to ask for 2 decimal precision, which means ready your calculators. We are going to use the function ln(x), interval 1 to 6, with 5 rectangles. And a 2 decimal precision, you will have to use the calculator to do the ln for most of these. Let's see what you get. And you can use the left. You know what? Let's split up the room. The people to my left use the left point. People on my right use the right point. So you guys, 4 of you, use the right points, which is the sine graph, and you guys are using left points, which is the first example we did. Other parameters are the same. Let's see how it goes.
The reason I want to ask you is like what kind of software you like to use. Do you have for calculus like Python or
No. No, you can. There are different software for different types of mathematics, but it's a programming language. Like math can have a programming language. There's a lot of that stuff. On it.
and like you don't do something mathematical for you know I think you are down to otherwise
Yeah. It says when you open the email, the link I sent you, it says above, find out, if you find out you have some link there, create an account, so then I will see that, so it has to be like evaluated you, and then they know, and then you know, they know the part of the scene. Otherwise,
Yeah, I want to pay $1,000.
$1,000, yeah.
and we're inside of them.
Sorry?
Which side of them will you inside you said the
Well, this is the right side. This is the right way.
points on the right side or the rectangle goes to the right?
It's points on the right, so the rectangle is that way. So when you do the partitioning, right, you look at the rectangle, and it's the right point is in charge. So you guys left point.
I just got to get an A on this exam.
And you gold, right?
Me too. Yeah.
Like
don't, but it's gonna jump up a little bit. Wait, how much points did you say I have last time?
You did 14.
Yeah. What's the 7? Wait, was it 14 or was it 11? Okay, 20. I'm so lazy. I was section. Yeah, right. For like 80, like yeah. It's so lazy. Can I have this point? What if he does that? He probably does.
Because it's 1, the area is equal to the sum of the lines. Because the difference is 1.
I wish you could control this person's meal. Because that's not even a meal. Those naked stomach would devour that. The worst is someone's meal. Like that wouldn't even like fill like a little bit of you up.
Yeah, we're talking about
Yeah.
one chicken wing.
4 greens. Yeah, those are. Come on, like
So useful if they did everything.
and I bet that meal right there is about like $20-$30 just for that.
It's so stupid.
Yeah.
The worst is when just now, I got the entire base.
That looks good. Yeah.
What I had last night, minus oh, I hate that. And
The mom sent me to cooking
like a bunch of stuff that was added to 20% of the base. And they went to like some place, yeah, no, they got destroyed, and then they got animated. Yeah, right? Seriously, if you get more
right, cranes or that. There's a good place in Prince up there. You make yourself food. I don't know the right one. I don't know the right thing to make. Don't you need a nice little thing?
Alright, you go. Apparently, nice.
yeah, I gotta say, those are crushing.
I'm not as good as you.
It's giants, like,
Shoot. This is still up to you. This is still up to you, by the way.
Dude, I don't know what to put. He never says that thing here anymore.
All right, so 2 decimal precision on this one. We are going to draw the graph. It goes through 1, and then we have 2, 3, 4, and 5. I knew it's going to be this way because 6 minus 1 over 5 is 1, right? So delta x is 1. Easy.
Is it a negative one? Oh, wait.
So, if we are working on right points, oh wait, I needed one more. Needed one more. Ends at 6. There we go. Perfect. So what do I have? Area is approximated by delta x is 1. So delta x is 1, we can completely ignore it. It's just f. So f of 2 plus f of 3 plus f of 4 plus f of 5 and plus f of 6. 1, 2, 3, 4, 5 rectangles. Nice. Which is equal to ln2 plus ln3 plus ln4 plus ln5 plus ln6. And I'm going to put all of this in the calculator in one shot and just look at the 2 decimal. Yes?
Okay, so do it that way. So I did the separate LNs.
Oh, then you round each one, and then, yeah, the rounding error piles up.
Yeah.
Two decimal precision, 6.58. I to the nearest hundredth. Cents, right? What happened? All right. Two decimal place precision.
Professor, what about on the test you give us a problem like this? This, for example, right? If I put 7, would it mark all the way wrong?
It's not all the way wrong, but it's. Why would you put 7?
Yeah, 7.00.
I don't know. I'm just wondering how many points would you like take off of the problem?
Oh, I don't know. That depends on the mood. The better the mood, more the points. All right.
Yo, pizza party during the test?
During the test?
You can do it after.
No.
During. I'll be
During.
No way. I'm too distracted. I'll be eating all the pizza instead of my test.
Can you not eat and think at the same time?
I can't.
Whoa.
Are you ready?
Oh,
4.
oh, you can.
The story on sums.
It's cruel to make a man choose pizza.
So if I quickly jump to Calculus 2 for the stuff that we did last night, you see this symbol here. And then if I jump into any of the lessons from Calc 2, you are going to see that symbol everywhere.
Summation sign.
Yes. So this symbol is everywhere. Differential equations will have it as well, and later on linear algebra. So the symbol is extremely important, and this is the time for you to learn what it is and how it works. It's used a lot. So sums. We are starting with the letter, which is sigma. It's a capital letter, and it means sum. the way it works is you will say that summation, well, I starts from 1 to, let's say, 9 of I is 1 plus 2 plus 3 plus 4. Why did I choose 9? 6. It's fine. I'm already tired. Plus 8 plus 9. There we go. But then we can actually have a formula that depends on the counter. I can use n. Let's say starts at 3 and goes to 6. See, I learned quickly. Let's say you have 2n. That's going to be 2 times 3 plus 3 times 3, 2 times 4 plus 2 times 5 plus 2 times 6. So observe that this n is the one that clicks. This is discrete. It's used for computer science, obviously, but it's used also in electrical engineering and other engineering areas a lot. So you see, I hope you guys see the structure. This says 2n, and here's your 2n, 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 where n goes 3, 4, 5, 6. So in a summation symbol, all you do is you follow the formula, but then you have to use the counter and move between the values. So here's one for you to write out. So n goes from 2 to 5 of 3n minus 1. So what is this? Now you can actually compute this, right? You can add all of the multiply and sort everything out and get a value if you're interested. Good, keep going.
Oh, I'm so hungry.
That's why you
Bro,
make
it's
that.
so funny. We did like a little recorder of this last week. It's all
Just
a
like
special
Lou's
moment.
just sighs. Just
Count one with Nick. Bloopers.
Yeah,
Behind the
that's
scenes,
it.
behind the
That's it.
scenes. He owns the making of Calculus1.
Yeah.
that would have to be me. Should be saying 45 earlier. Like we had.
Feel like starving. Can't even think right now.
That would be
So 3 times 2 minus 1, 3 times 3 minus 1, plus 3 times 4 minus 1, plus 3 times 5 minus 1. If you want to compute this, 6 minus 1 is 5, plus 9 minus 1 is 8, plus 12 minus 1 is 11, plus 15 minus 1 is 14, and when you add all of these, we have 25, 38.
Quick one. So basically, you're starting at 2, since you need to end at 2, and then you just keep going until 5, right?
Yes.
Messed up, bro.
6 minus 1 is 5, 9 minus 1 is 8, 12 minus 1 is 11, 15 minus 1 is 14, you have 25, 30, 38.
Wouldn't it be 3 parentheses, 3 minus 1, close parentheses, plus, and then you would do 3 minus 1 in the parentheses, then it would be 2, and then you do the multiplication.
No, it's not this.
Oh, I did. Wait.
Times 3 first.
Order of operations.
Order of operations, yes. All right, one more. Let's go back to I counter. 1 to 5 of I squared plus 1. This is the introduction to summation. Guys, are you done?
Yeah.
58? All right, so we have 1 squared is 1 plus 1 is 2, 2 squared 4 plus 1 is 5, 3 squared 9 plus 1 is 10, plus 4 squared 16 and 1 is 17, plus 5 squared is 25, 26. Right? So what do we have? We have 31, 41. This is 60.
Wait, so when it says I equals 1, then you also include the value.
Yeah, you have to start from the value.
Okay, I got it. Got it.
All right, now, these sums, you have to understand that these sums are just addition of numbers. So if I have a summation of, let's say, 3i, where I goes from 0 to 7, I will have 3 times 0 plus 3 times 1 plus 3 times 2. You see that you can factor out 3. So if you have a summation of c times some function of I, you can kick c in front. You know that you can kick constant in front of integral. You can keep constant in front of derivative. You can keep constant in front of the limit. You can keep constants outside of the sum as well, because it's just simple factoring, actually, that happens. So you can do that with sums as well. And then there are other properties of sum that you will learn as you keep learning about mathematics. Right now, we just wanted to understand what the sums do. So it's a shorthand notation for us to write. Now, these sums could also be infinite. You are going to deal with that in Calculus 2 most of the time. And then they can have numbers underneath, they can have functions underneath, and all of those kind of things. Then they can be nested. You can plug one sum into another sum, and there's a lot of cool mathematics that you can develop on top of what we have here. Now, why do we need all of this stuff? Why did we talk about sums? We talked about sums because of the sentence which I wrote earlier, and that sentence said that if you are approximating area under the curve using the rectangles, the more rectangles you use, the better the precision. And then I asked you how many rectangles do we know for exact area, and you said infinitely many. So now what we are going to do is we are going to write the formula which will show infinitely many rectangles. So what I have here is the good old picture from before, and then we cut in half, and we cut in half, and we cut in half, and we cut in half, right? And we keep cutting this in half, and every time when we cut in half, these rectangles become smaller, and with the smaller rectangle, right, eventually what's happening is that the dx is going to 0 as n is going to infinity. So that is the idea. And as this is happening, when these two things both check, right, and they have to check, because recall this, delta x is equal to b minus a over n. The top is constant. So if this is going to 0, this better be infinity. Because when you divide a constant number by infinity, you get 0, right? So delta x is going to 0 because the number of rectangles that you are enforcing is going to infinity now. Now, what is happening with our calculation in this respect? Yep. So good. Look what's happening now. I'm going to start to build this special formula by claiming that I have the height of the function times delta x. So would you all agree that this is only one rectangle? Right? Function times delta x. That's one. And then I'm going to add all of them. And then what I'm going to do is to say that the finite number of rectangles which I had before, which was 4 or 6 or 8, boom. You see that? So this is how you build the formula. I'll do it one more time from scratch. I start with a single rectangle. I call this f of xi times delta x. So this is a single rectangle, just one. And then I add to how many I have. Note that the counter I will keep changing the input x1, x2, x3, x4, right? And then I'm going to deal with the finite amount of rectangles which I used to have in the previous examples. I'm going to send that to infinity. Guys, what you have over here is definition, the limit definition for the integral. The definite integral from a to b f of x dx, where this dx is that dx. And now you finally understand that this dx is not there for decoration. That dx is the width of each rectangle. And if you are not writing that dx there from theoretical point of view, you are not doing anything actually then, right? Because you have a function which is the height, but you are not multiplying that by the width. So that's the reason why the delta x must be there. It must be there because dx is the width of every of these rectangles. Now, how big is it? It is going to 0. It's infinitely small. That's how wide dx is, but we have to have it.
So that means that if you didn't have that limit there, that would be a general formula to get automatically get the area. It's the summation of the.
No, this is exact area. So I'm boxing this as the most important formula, and I just say exact area. This is known as the Riemann Integral. German mathematician Riemann, who figured integration out, figure out all of these applications, and then open the doors for us to actually work on, invite integrals into physics and engineering and figure out the technology that we have today. So now, let's solve a problem. You remember how we had a problem here which said x squared plus 3 on 0 to 4. X squared plus 3 on 0 to 4. This problem says find exact area. Find exact area. Start on a fresh page. It takes some space. Ready? We are supposed to. Is the stream still on? All right, good. So what do we have, guys? Look at this.
Yeah.
So we are looking for the exact area. We are supposed to compute limit as n goes to infinity of the summation I goes from 1 to infinity to n f of ci times delta x. All right. Well, delta x is easy to compute. We know the formula for that. That's b minus a over n. So we have 4 minus 0 over n. It's 4 over n. All right, we got that part. Right? The next part is for us to figure out this xi. I don't know why I put ci, xi. So what's xi? Xi is every single number in a mix. Ooh. And how many do we have? We have infinitely many. So now, let's discover what is the formula for xi. If you think about this, your function is going to start somewhere with a, and then it's going to have infinitely many of these divisions. Your a is x0, and the next one is x1, which is delta x away. And the next one is delta x away for x2. So you are starting xi at a plus counter times delta x. Let's say you want to go at x3. How far is x3? It has to start at a, wherever a starts, and then it has to be 3 delta x's away. 3 delta x hops. First hop is x1, x2, x3. So x3 is 3 hops away. So if I want to get x3, then that's a 3. If I want x5, then that's a 5. Does it make sense? So what we just made over here is the formula for xi, and for our problem, xi is a is 0 plus I times 4 over n. So for our particular example, we have 4i over n. Make sure that you are understanding that this I is not a complex I. It's just a counter I that we use in discrete mathematics.
So mathematically, how is this going to be used to compute an actual value if it loops back on itself because the n is a changing value that goes to infinity?
Well, remember that we have the limit, and that's going to smooth it out. So now we have everything, and we plug everything in. So now that I have xi, I can compile f of xi, which is 4i over n squared plus 3, right? Was that the equation? X squared plus 3? Yep. So I take xi squared plus 3, right? So this over here is xi squared plus 3 because that's the formula that was given to us. And we work that out as 16i squared over n squared plus 3. Great. I have everything that I need. All the building blocks are there. Observe what I have. Limit, summation, or limit n goes to infinity, summation 1 to n. And then I have f of xi times delta x. Now I need to plug this in. So limit n goes to infinity, summation I goes from 1 to n. I always want to skip a step. And then f of xi is 16i squared over n squared plus 3 times the delta x, and delta x was 4 over n. And now we need to compute this. Welcome to Calculus 1. Yeah, that was the setup. So now we are computing the problem. Limit n goes to infinity, summation I equals 1 to n, multiply through 16 times 4, obviously 64i squared over n cubed, plus 12 over n. Right, summation works on all of this. The next order of business is to split this into two sums, right? You have a plus, so it splits into two sums. So limit n goes to infinity, we'll put these brackets, you get I goes from 1 to n of 64I squared over n cubed plus summation I goes from 1 to n 12 over n. Great. Next order of business is to understand that you have a variable I, variable n, but your summation only cares about variable I, because variable I is the variable for the sum. Variable n is important for the limit. That means that you can kick n as a constant outside of the sum. You can't kick it out in front of the limit because limit will operate on n. Sums operate on i's. So I can go and say 64 over n cubed summation I squared plus 12 over n summation of 1 to n. Because, right, there are no i's there, but you have to have something, right, in there in the summation, so we just leave 1 there.
64 over the summation, would that be still I equals 1?
Yeah, it is I equals 1. I'm just not writing it anymore because now we know it's I. Now, we are going to consult, I'm not sure which page it is. There are 4 formulas somewhere in your textbook. There they are. There are 4 formulas on page 340, which are the bridge between the summation and its sum. So you see that we have a summation of I squared. Summation of I squared, which is k squared, you can use any variable you want, is this. So we are going to replace those 2 sums. We are going to replace those 2 sums with what the actual answer is. So this sum is going to be n plus 1, 2n plus 1 over 6 plus 12 over n. And the next summation here, using the formula, is Cn, so that's 1n, so it's just n. And we converted this problem to a limit problem now. If you observe carefully, well, let's just cancel what we can, so these n's die. Limit n goes to infinity. 64 and 6 will cancel by 2. So I'm getting 32, n plus 1, 2n plus 1, divided by 3n cubed, plus 12. Now observe that the leading term, when you FOIL all of this, is 2n cubed, times 32 becomes 64n cubed, divided by 3n cubed. You know when you take the limit goes to infinity that n cubed over n cubed just gives you 1. So this becomes 64 over 3 plus 12. 64 over 3 plus 12, that's 36, so 100 over 3. The exact area is 33 1/3. So we did this problem to demonstrate the procedure of how we use the limit, how we use the Riemann sum to find exact area under the curve. And it is very systematic, because when you know the formula, you look at the ingredients. I can get that, I can get that, therefore I can get that. We plug all of those in. So here is me getting dx, here is me getting xi, here is me getting f of xi, right? So all of these features, and then finally here it is all plugged into the formula. From there, distribute, and break all of these pieces. Use the formulas to convert, right, the summations into the sums, and then apply the limit to get the final answer. Or, in section 5.2, which is the next section, you will say for the same problem, integral of x squared plus 3 computed from 0 to 4, which is x over 3, x cubed over 3, plus 3x computed from 0 to 4, which will give you 64 over 3 plus 12, which is 100 over 3, which is 33 over 1/3. I know, so it's one or the other.
Oh boy. Can the same guy figure out both?
Of course.
Yeah.
You remember the long limit definition of the derivative?
Yeah.
Well, you just witnessed the same thing for integrals. How often do you use the definition for the derivative to find the derivative? Never, right?
6x. That was the answer.
No.
Just about it.
I should make the top. I should make the top way. It happens.
He's not liking you already.
This means it's first a derivative. Integral of 4 over 0.
Oh, that's computed at. Well, that's 5.2. All right, guys. So we're going to take 5 minutes break, and then we're starting 5.2.